in the last lecture we were looking at enclosures with gray, diffuse, isotropic surfaces. So, in this case, because of the assumption of diffuse isotropic surface and gray surface, the problem became quite simple. And because the surface was gray, we were able to avoid the wavelength integration. So, we got a very simple electrical analogy. Wherein we saw that the geometric resistance between any two surface is nothing but 1 over AI Fij, and the surface resistance is 1 by epsilon I AI. So, this resistance is occurring because the surface is not a black body. So, there is resistance to flow of heat, and this the first term, the geometric resistance is coming in because of the relative configuration between two surfaces. And using this idea of geometric and surface resistance, we were able to draw a typical example of surfaces which involved a battery, a surface resistance, a geometric resistance, another surface resistance, and the second battery. And if you have 3 phase enclosure, we drew 2 more geometric resistances, and then we had another battery here. So, this is radiosity point B1, this is radiosity point B2, radiosity point B3. So, between the 3 radiosity points, you have the geometric resistance, while between the radiosity point and the black body radiation is the surface resistance, and so on. Okay. Now, we also applied this for a few simple examples, and so I will illustrate one example which is of great relevance to many situations in engineering. Imagine a convex object, a cylinder surrounded by a general object. This surface 1 and this surface 2. So, there are only 2 surfaces, we can neglect this part. So, then we can draw our electrical circuit for this case as one battery here, this inner one sigma T1 to the power of 4. So, 1 minus epsilon 1 A1. Then you have 1 over A1 F12. F12 is 1 because surface 1 is convex and is surrounded completely by surface 2. So, any radiation leaving surface 1 has to be surface 2. So, F12 is 1, that is taken care of. Then you come to surface 2 is geometric resistance, and finally, you have the battery here. Okay. And if you want to simplify this, you can write this energy transfer from 1 to 2 as sigma T1 to the power of 4 minus T2 to the power of 4 into A1 divided by this term on by epsilon 1 plus A1 by A2 1 by epsilon 2 minus 1. This is a very useful result we have here. Now, let us look at some limiting cases of this to understand what it implies. Now, suppose the object 1 has much smaller area than surface 2. This is typical in engineering. Imagine a steam pipe going through a room. The pipe area is very small compared to the room area. Okay. So, if A1 is much smaller than A2, you can neglect the second term. Then Q12 becomes epsilon 1 sigma into temperature, the difference in potential. Now, what it means is that if the room area is much larger than the area of the pipe here, then epsilon 2 value is not important. Whatever the value of epsilon 2, the heat transfer rate will not change. Now, why is that? Now, this is because if the surface 2 is much larger than surface 1, any radiation leaving surface 1 after multiple reflection will reach surface 2. Okay. Because of that, it does not matter what the reflectivity of surface 2 is, whether it is 0 or 1, it does not matter, because ultimately radiation leaving 1 will be reflected into and come back to 1 by multiple reflection. So, if surface 2 is very large, the radiation ultimately will. So, the rate of radiated heat transfer between surface 1 and 2 is not dependent on the reflectivity or emissivity of 2, but only on the emissivity of surface 1. So, this is a very useful result to have, which means we need not really worry about the exact value of epsilon 2 or the emissivity of the room, and essentially it means we can treat the room as a black body. This because any radiation leaving 1 ultimately is absorbed by 2 at some point, okay, either out of 1 or multiple reflection. So, as far as surface 1 is concerned, surface 2 is effectively a black body. So, this is a very important concept, and we will come back to this concept a little later when we derive effective emissivity of certain objects. So, this is the result that is worth remembering. So, this result is same as if epsilon 2 was equal to 1. So, equal to 1, this term drops out and you are getting the same result. So, although surface 2 is not a black body, if its surface area is very large, it is behaving like a black body, and the rate of heat transfer by radiation from 1 to 2 is independent of the emissivity of surface 2. So, this has both practical relevance as well as provides an understanding of the role played by the area ratios. If some surface has a large area compared to another surface, then the second surface really is in a way behaving like a black body. Now, let us take another example now, a more practical example of relevance to mechanical engineering, which is radiative transition in furnaces. A typical furnace, and here we are talking of metallurgical furnace, not one used in power plant, has a roof and a floor, and some walls, side walls, which are refractories, whose job is to really reflect the radiation and avoid leakage of radiation. This is also refractory. Suppose you call the roof as surface 1, floor as surface 2, and the side walls refractory as surface 3. And not generally we assume that these are insulating, so adiabatic surface. No heat is transferred through the surface, or heat leakage is small. Let us take an example where emissivity of this is 0.8. Let us say temperature, just an example, 1000 Kelvin. Surface 2 emissivity is 0.6, temperature is 500. And you want to know the rate at which heat is transferred from the roof to the floor. Now, since surface 3, this surface 3 is adiabatic, so when we draw our electrical analogy, although we will come to surface 3, but since surface 3 is adiabatic, no heat flows through it, okay, Q3 is 0. So, any heat that is going from 1 to 2 either goes directly or goes by reflection through the refractory back here. So, it is nothing but a simple series parallel circuit, which all of you have seen in electrical engineering, and this is the surface resistance, geometric, surface, geometric, and geometry. So, what is happening here is not relevant because no heat is flowing through. So, you can easily solve for this parallel series circuit, and the final expression for heat transfer from 1 to 2 will be sigma T1 to the power of 4 minus T to the power of 4 into A1, and let us for convenience assume A1 equals A2 equals A. Both the surfaces have same area. It makes things a little simple here, algebra, and you have 1 by epsilon 1 plus 1 by epsilon 2 minus 1 plus F13 plus F23 divided by F13 into F23 F12 into F13 plus F12 into F23. So, all possible combinations are here because you have reflection from the adiabatic side walls. And we can substitute numbers and get an answer, which we will do presently, but let us understand what is the role played by refractory. There are various ways to look at this. And suppose F12 is very small compared to F13. That's say 3 is a large refractory area. So, F12 is small compared to F13, that is F13 and F23 are very large. These are large quantities here, and so this quantity will dominate your compared to F12. So, if we only retain this term compared to these two terms, then you will getting a simple expression in terms of 1 by F23, 1 by F3 and this. So, clearly showing that essentially what we are saying, that this resistance is very small. And because F13 is okay, let us take two cases. One is the F13 and F32 are quite small, then the resistance is very large, most of the flow occurring directly to this. The other extreme case is where F12 is large. So, this is the open circuit and the flow essentially goes through that. Both these are possible in this situation, and both do occur in real world, both situations. If the two plates are very close to each other, then F12 is close to 1 and these two are close to 0. So, this is an open circuit. And on the other hand, if these two are very far apart, F12 is very small, this is an open circuit and the flow goes like this. So, both these examples can be shown to occur in practice. And so, in this case, let me just complete this problem. For this temperature that is given here, we need to calculate F12, and F12 you can calculate easily by the Hartle's cross-string method. If you do that, you will get out answer is 0.5. That you can see very easily, because the distance between the two plates is 3 meters, and this is 4 meters, and this is 3 meters, the gap. So, this will be 5 meters, this will be 5 meters. So, you apply the cross-string method, the sum of the cross strings minus sum of the parallel strings divided by twice, you will get 0.5. Substitute that into this equation along with the values of emissivities and temperatures, you should get a number like Q12 is around 170 kilowatt per unit depth of the furnace, assumed to be very long in this direction. Now, I can use the same formula to look at a different example. Suppose you have a large room containing a steam pipe and a water pipe. Steam pipe is 1, water pipe is 2, and the inside of the room is surface 3. And the main requirement here is that A3 main condition is room is very large, typical in many situations in industry. A3 is much more larger than A1 or A2. This is a 3 surface enclosure, and you can assume room is adiabatic. And since A3 is much greater than A1, A2, all of you can visualize that F12 is much less than 1, because the two pipes are far apart. So, from the previous exercise you have done, you will get a very simple electrical circuit. This is 1 minus epsilon 1 A1 1 minus epsilon 2 A2, 1 by A1 F13, 1 by A2 F23. So, we have made the open circuit because F12 is very small. So, your flow is really occurring through the walls to the other side. So, you can solve this very easily, and the simplest way to do is to assume F13 is equal to F23 approximately equal to 1. We neglect radiation exchange between 1 and 2, we assume most of the radiation emitted 1 reaches 3 and not 2. If you do that, these two are 1, then you have a very simple result here. And let us make life easy by assuming the two areas are same. So, 1 by epsilon 1 A, this is 1 over A now, there is another 1 over A, and you have 1 minus epsilon 2 A, and the second battery. So, you can easily check that these will cancel out, this 1 over A will cancel minus 1 over A here and so on. So, we have a very simple expression for the radiation between two pipes, which will be Q1 to 2 equal to sigma T1 to the power of 4 minus T to the power of 4 into area of the pipes is the same. So, that is the answer you get for this very unusual case of two pipes far apart in a big room, and then ultimately the heat transfer is determined by the emissivity of the two, this one. Emissivity of the wall is irrelevant, which is not surprising because the room is very large. So, similar to what we saw in the case of the furnace, the refractory walls are large, the emissivity of the walls are not relevant, same thing here. So, the room is very large, it does not matter what emissivity or reflectivity it has, ultimately it behaves effectively like a black body. And so, the heat transfer between 1 and 2 depends probably on the emissivity of the two surfaces. So, if you want to minimize the heat transfer from the steam pipe to the water pipe by radiation, you will just ensure that keep the emissivities very, very small, or keep the outer surface of the two piping as highly reflective. This is what normally done. All these steam pipes in the power plants and industries are usually insulated and then further covered with a reflective film, so that its effective emissivity is pretty small. And you can see that it can be controlled for example, if we take emissivity of the order of let us say 0.01, maybe a bit tough to achieve, but it not impossible. So, this is 100 per 100 200. So, you reduce the heat transfer between the two pipes by a factor of 200 compared to if they were black body. So, that is a large reduction. So, this shows you how one can control radiative transfer between surfaces by adopting surface properties in order to control the heat loss. So, this is an example, and in the last class we saw how providing a shield to a thermocouple also reduces the error in the estimate of heat transfer. So, this is an example illustrating the use of electrical analogy and simple approximations to simplify the problem that we encounter in solving problems. But notice that if the number of surface in the enclosure becomes very large, then there could be some problem in handling such cases. Now, before we do that, let me take a few examples of relevance in the case of shields. So, we had looked at thermocoupled shield, but let me look at another kinds of shield. Suppose there are two parallel plates, 1 and 2, both having the same emissivity epsilon, and these are infinite parallel plates. So, we know that heat transfer rate between the two infinite parallel plates is nothing but T1 to the power of 4 divided by 2 epsilon minus 1. So, this is one result. So, one can see that if suppose we had kept the epsilon very low, let us say 0.01, that will be 200 here minus 1, 199. So, you can reduce the heat transfer by a factor of 200 almost compared to the heat transfer between two black plates. But suppose you want to decrease further the rate of heat transfer. So, between the two plates you can put a shield. So, this is plate 1, this is plate 2. Now, you put a shield. The role of the shield is to reduce heat transfer on this plate. Let us say sheet also has emissivity epsilon on both sides, the shield. Now, you can draw the electrical analogy here. There are multiple, this one, it can easily be shown that Q12 in this case will be sigma T1 to the power of 4 minus T to the power of 4 divided by 4 epsilon minus 2. Now, this coming in because between these two parallel plates it is 2 epsilon minus 1, and between these two parallel plates the same, and the resistors are added, you get this. So, clearly Q12 with shield is equal to Q12 without shield divided by 2. So, essentially if you put one shield between two parallel plates with the same emissivity, and the shield introduces also the same emissivity, then it cuts down the radiation transfer by half. By the same logic, if you had n shields, many shields, n shields like that, then one can easily show that Q12 will be equal to Q12 without shield divided by n plus 1. The 0 shield, of course, you get back the old result. With one shield you get 2, which is what we saw. So, 2 shield 3. So, it is quite clear that you can bring down the radiation heat transfer between two surfaces by quite a large margin by having a large number of shields. Now, this is what is done in the case of insulation. So, you can have hundreds of these thin plastic layers coated with aluminum. So, you have a coating of aluminum on both sides, which makes it highly reflective. So, epsilon is pretty low, and in addition you are having a large, suppose n is in hundreds. So, you can bring down the heat transfer rate by a factor of 100. Okay. So, previously you saw that with a single shield or even without a shield, if the epsilon was very low or reflectivity was very high, you can cut down the heat transfer compared to 2 black bodies by a factor of 200. Now, on top of that you can have 199 shields, then you are further reducing by another factor of 200. So, it is a very effective method. This is the most effective way of radiatively shielding a surface from heat loss, and is used routinely in both satellite applications and other applications. This is called a blanket. It is essentially hundreds of plastic layers which are highly reflective, and it is a very inexpensive as well as very low weight insulation, because thin plastics are not very heavy. So, this is widely used and you may have seen it in many applications. So, this is a fairly effective technique to control heat transfer. Now, let me give a practical example of another insulation which all of you are familiar with, that Thermos Flask. In a Thermos Flask, you have an inner cylinder and an outer cylinder, and I think I will draw a better figure here. All of you have used this Thermos Flask for carrying hot coffee, and of course, here is a cap. Okay. And let us assume that the emissivity of the two surfaces is kept low by coating. So, what is done is these two surfaces are silver coated, so they are highly reflective. So, the outside may be at a temperature of 300 degrees Kelvin, room temperature, and inside can be, with hot coffee, maybe 370 Kelvin of that order, and there is heat loss from the here to here, and this gap between the two silver surfaces is evacuated, so that you essentially minimize the convection and conduction losses. And then the only loss left is radiation, and it can be shown that if this surface 1 and this surface 2, we will discuss later, you can show that heat transfer from 1 to 2 can be treated as between two parallel plates, and then if you assume that the surfaces are gray, diffuse isotropic, so this is one result, but we will derive this result more rigorously in a subsequent lecture when we deal with highly reflective coating. Now, if you treat this as a diffuse isotropic surface, of course, you are not really making the right assumption, because you must recognize that the surfaces are highly reflective and hence cannot be treated as diffuse isotropic, but we will show later that the answer we get by assuming diffuse isotropic is not that different from actually accounting for the mirror like reflection that occurs in this case. And now let us look at some numbers for this case and let us see what it looks like for a Thermos Flask situation. And as I said, we have kept down the radiation and radiation only dominant mode of heat transfer here. We neglect the heat transfer by conduction and by convection, because we have essentially reduced them by evacuation. But the key issue to remember is that ultimately, even if you control conduction totally and only radiation, let us put some typical numbers here and see what are the numbers. Suppose you assume surface 1 is at 88 degrees centigrade, that is the surface 1, okay, and we assume surface 2, which is the essentially the ambient, to be on a cold winter day 16 degrees centigrade, and we assume the emissivity of the order of 0.2, which is achievable with silvered surfaces. Assume all that, you will find that Q12 is of the order of 5.7 watts per meter square. This is quite small, okay. And if you actually assuming this is the only heat loss and you can add a little bit of heat loss due to conduction, you will find for this heat loss the coffee should remain quite warm here for many days. But in reality, most of you have experienced that in a good Thermos Flask, the coffee remains hot only for maybe 8-9 hours. The main reason why our calculation is too optimistic is that the heat loss to the top, heat loss to the cap, which is very large. So, the key thing to remember is that from this exercise is that the difference between a good Thermos Flask and average Thermos Flask is the design of the cap, because one is able to control very closely the heat loss through the side by controlling conduction, convection as well as radiation. So, the main leakage of heat is now through the cap, and the cap design becomes critical. So, between a good design and a bad design is how well the cap is designed to prevent evaporative heat loss through the gap here. Okay. And so, you will find if you carefully look at the design of a costly Thermos Flask and a not so good quality, you will find really the good Thermos Flask, the heat loss through the cap is being controlled by a very careful design of the cap, which is the major heat loss path. Okay. So, this also gives you a very good idea as how sometimes you may miss out when you look at the design of Thermos Flask, you may not realize that the cap design is the most critical. You may think that keeping the cap evacuated is a major issue. That problem has been solved a long time ago. Keeping the evacuation good is not a problem. Silvering is not an issue at all. And so, the only issue is really the only movable point, there is a cap. The cap has been so designed as to reduce the evaporative loss. So, this kind of calculation helps you to highlight the role of the dominant parameter. Okay. So, let me now move on. So, we have looked at shields, we have looked at Thermos Flask. Now, let us ask this question. Suppose you have an enclosure consisting of a large number of surfaces, not just 2, 3 or 4 that we discussed in the last 2 lectures, then we cannot resort to electrical analogy. We have to solve it on the computer using the power of matrix algebra. Okay. So, let me illustrate how this method is worked. This method is called the Radiosity method. So, what are the problems that we formulate with a large number of surfaces? We treat radiosity as a main unknown factor. We solve for radiosity by matrix inversion. So, you have to set up the whole equation in terms of radiosities. What is the radiosity of surface J? Bj is nothing but emissive surface J, emissive power, plus what is arriving in surface Hj. We also know that Hj, what is arriving in surface J, is what left surface K and how it arrives surface J, summed over all surfaces K equals 1 to n. But by using reciprocity, this can be made to look simple. Hj, you write this as Aj Fjk, using reciprocity. So, Aj is not being summed over, so it cancels out. So, you have simple expression in terms of Bk Fjk. Okay. Now, what is the advantage? Because now you can write Qj, heat to be removed, as radiation leaving the surface, that arriving times area of surface. You can also write it as radiation emitted minus radiation absorbed for a gray diffuse azimuthal surface alpha j equals epsilon j. So, this is actually absorptivity times irradiation multiplied by Aj. Now, what we would like to do is essentially eliminate irradiation from all this expression, because that is unknown quantity. So, write everything in terms of radiosity. So, that we can do by eliminating Hj from this equation. So, we get 2 equations now, which is Qj is equal to epsilon j Aj sigma Tj to the power of 4 minus Bj divided by 1 minus epsilon j. So, this relates the heat transfer to the temperature surface and the radiosity. Similarly, you can write Qj also as sum over all k surfaces 1 to n, radiosity of surface j minus radiosity of surface k into Aj Fjk. This we already derived when talking about electrical analogy. So, suppose we treat radiosity as an unknown problem. Suppose we have n surface enclosure, and let us say in some surfaces temperature is known, but the heat flux is not known. In other surfaces heat flux is known, the temperature is not known. So, if that is the case, we can rewrite our formulation as follows: sigma over k this is the Kronecker delta, that is when j is not equal to k it is 0, when j equals k it is equal to 1. F j k 1 minus epsilon j into b k. This is just rewriting the expression really by substituting q here and getting everything in terms of b. So, here is a case where if I know the temperature, this is a known quantity, I write everything in terms of unknown radiosities and these are known, the shape factor and surface. On the other hand, in another surface where the flux is known, I will write this expression. So, there are two equations we have. So, we use equation 1 wherein the temperature is known and use equation 2 where the heat flux is known. So, on any given surface, we expect that either the temperature is given or the heat flux is given, and in surfaces in which temperature is given, we want to know the unknown heat flux to be supplied to keep the temperature at that value, and in surfaces where heat flux is given, we want to know what temperature that surface will attain. So, in the first case the unknown is Qj, in this case the unknown is Tj. But we could solve for the two unknowns, but then we prefer to solve it in terms of the unknown radiosities, and once those radiosities are known, you can go back to this equation, and if Bj is known, you can calculate Qj, and if Bj and Tj are known, calculate Qj, and if Bj and Qj are known. So, this equation can be used to calculate Tj or Qj, whichever is unknown, once you know Bj. So, this is just a matrix generation technique, very simple methodology today with the computer available. So, broadly you have a matrix of unknown and these are the Bj's, these are either Qj or epsilon j sigma t, one of the two depending on which is specified, and accordingly the matrix element will change. So, you invert the matrix to obtain Bj. So, that is the main spirit of the radiosity method. So, once your shape factors and emissivities are known, and in those surfaces where heat flux specified, you put one matrix element, and wherein temperature specified, you have another matrix element. You know all the matrix element, invert the matrix, get the radiosity. Once you know radiosity, you can go back to the previous. So, where the radiosity, where the temperature is specified and we have estimated radiosity by inverting matrix, we get the flux. Where flux is specified and radiosity is estimated from inversion, you get the temperatures. So, this equation is used to solve for either Tj or Qj given the Bj from the inversion matrix. So, these are the matrix elements here in these equations, and this can be completely automated. So, there are standard now software available which will solve for this, and the advantage, as all of you can realize, is today computers can invert matrices very quickly. So, you can solve this kind of problem for 100 or 200 surface enclosures or even 1000. Now, you might wonder why should we be solving for enclosure with 100 surfaces. Now, that is normally the case, because even though the enclosure may contain only maybe 3 surfaces like in a furnace, where we had an example sometime back, this one, although there are only 3 surfaces here, but it can turn out that the temperature of the 3 surfaces is not uniform, they are non-isothermal. If they are non-isothermal, you are better off dividing this into many surfaces, maybe 10 or 20, as many as you would like to do, so that within each element you can assume isothermal surface. Similarly here, this is not going to be isothermal, so you divide it into many parts. So, you may divide it into 100 parts here, 100 parts. So, you have a 300 surface enclosure, not too difficult. Once you know the shape factors and you know the surface properties, you can easily invert the matrix to get the 300 radiosities, and once you know radiosities, you can get temperature or heat flux given the other quantity. So, this is now the fairly routine method in which problems are solved for radiosities, and this is the method which is the preferred method today. Although we discussed the electrical analogy, that is more for our attempt to illustrate the physical insight you get in drawing those electrical resistances. But as soon as you get into a situation where the number of surfaces is more than 2 or 3, the electrical analogy becomes not very useful, and it is much more useful to just use the radiosity method and just invert a matrix. Now, just so that we recall that this method is a useful technique, we will now go on to illustrate through the radiosity method the emissivity of a surface. So, this problem we want to illustrate the role of. So, suppose you have a large sphere with a small opening. Okay. Let us call this area A1 and the opening area is A0. Okay. So, the shift factor F0 to 1 is 1, because surface 0 is flat and it is only seeing this other surface. So, shift factor is 1. So, F1 to 0 is nothing but A0 by A1 by reciprocity, and the radiation leaving surface 1 and going through the gap is the radiation leaving incident on the surface. Okay. But you also know that radiosity 1 is nothing but emission plus reflection, and the reflection is of radiation that is emitted by 1. A0 does not emit radiation, A0 is only a imaged surface. So, only radiation emitted is by surface 1 and it is seeing itself F11. Okay. Since we know F10, we also know F11. Okay. So, F11 is nothing but 1 minus A0 by A1, right. Therefore, we substitute that here, you will get B1 as 1 plus 1 minus epsilon 1 A1 minus A0 by A1 into epsilon 1 sigma T1 to the power of 4. So, if you define the effective emissivity of this cavity epsilon A, apparent emissivity, is radiation leaving the cavity H0 divided by what it would leave a black body at temperature T1. Okay. And this you can calculate, it comes out neatly as epsilon 1 into 1 plus 1 minus epsilon 1 into 1 minus A0 by A1. Now, we are doing all this exercise because we want to illustrate the following point. As the hole in this cavity becomes smaller and smaller, that is, as A0 by A1 becomes extremely small, this term goes to 0. So, you get 2 minus epsilon 1. Okay. So, the apparent emissivity of the cavity reaches a limit which is epsilon 1 into 2 minus epsilon 1. This is a very interesting result, because you find that if epsilon 1 is 0.9, the apparent emissivity is 0.99. So, and epsilon 1 is large. So, you can make the apparent emissivity of the cavity approach 1. And so, this is the standard practice by which you obtain black body in the laboratory, by having a small hole in a large sphere, which is uniform temperature, let us say a copper sphere, and that small hole emits radiation like a black body. Because although the actual emissivity of the surface may be only be 0.999, what is coming out of the cavity will be approaching 1 as closely as you can arrange the area of the hole to be much smaller than the area of the cavity. So, this is standard practice of creating black body in the laboratory. So, with that we come to the conclusion of the discussion on gray diffuse isotope enclosures, and in the next lecture we will tackle a more complex problem of non-gray enclosures.